Hi, I'm Riley, and this is a presentation on simulating a hybrid rocket engine. Recently, I finished working on a program that does this, and I'm going to walk through some of the theory and ways that my program works. So, what is a hybrid rocket? That's kind of an important question. They're a hybrid between liquid and solid rocket engines, which basically means that they use a combination of liquid and solid propellants. Usually, it's a liquid oxidizer and a solid fuel, but you could have a solid oxidizer and a liquid fuel, but usually it's the other way around. Hybrids are less studied than liquid and solid engines, so that makes them kind of appealing from a research perspective. And then they're also feasible on a hobby scale. So an individual or a small team can build a hybrid rocket and fly one. Here's a video of the last hybrid rocket engine that I built. In the future, I want to build larger hybrid rocket engines, which will require some kind of computational design tool, which is why I worked on this project. So here's a really broad overview of how the simulation works. You have a set of input data. That's things like dimensions of the engine, your propellants, that kind of thing. And then it runs through the oxidizer tank simulation, the injector, which separates the oxidizer tank and the main combustion chamber, the fuel grain, which is basically where the oxidizer and the fuel react, and then finally the combustion and the nozzle, which is where your exhaust gases leave the engine and actually make thrust. And then it cycles through that for some amount of time steps. Usually it's in the few thousands for the resolutions that I've been running at. And then finally you have output data. It spits out all of the time steps as well as some total quantities over the entire simulation. So my program uses small discrete time steps. Basically, as you shrink the time step, you increase the accuracy or the resolution of your program. Here's a graph of different frequencies that I can run the simulation at. And here's a net impulse, which is one of the quantities that it can find. And you can see it kind of approaches some asymptote as you increase the resolution, which makes sense. I usually run it around 1,000 hertz because obviously you get diminishing returns, and higher frequencies require more computation and more time. Okay, so my program stores all of its input data in JSON files. That's just kind of what I already knew how to use, and it works pretty well. So there's two different files for storing the fuel values and then the user input, which is the dimensions and stuff. The fuel values, each fuel has a bunch of different important quantities, so they're just stored in a separate document. The input values are things like the frequency, which I kind of talked about, the masses of the propellants, the fuel grain dimensions, that kind of thing. Here are some of the fuel values. You have A and N are the regression exponents, which I'll talk about later. You have the density of the propellant, and then some of the chemical properties that have to do with the reaction between it and the oxidizer. And then here's some of the user input things. You have fuel grain dimensions, stuff with the oxidizer tank, stuff with the nozzle, and then stuff with the injector. Should be pretty self-explanatory. So the first thing that the program simulates is the oxidizer tank. For my simulation, it strictly simulates nitrous oxide. It wouldn't be hard to add other propellants, but nitrous oxide is special and that it sits at two phases when it's in the oxidizer tank. So you have a vapor and a liquid fraction. And this is really great because, other oxidizers like liquid oxygen have to be cryogenically cooled to have a liquid phase. Whereas nitrous oxide, you pressurize it to it's 700 and something PSI at room temperature. You already have a liquid right there. And then as the tank empties, you have liquid that will vaporize to fill the empty space. So you maintain a relatively constant pressure, which is good. Here you can see the phase diagram. And basically the nitrous oxide sits on this saturation curve between the liquid and the gas phases. That's highlighted in that orange color. What's cool about that is you can get pressure as a function of temperature or vice versa, which makes some of the math a lot easier. Here's a fun little thing you can do. Before the program actually starts simulating the tank, it has to figure out the mass fractions of the liquid and the vapor. So you have these set of equations at the top, and if you want to like pause the video and solve for these two things down here in terms of those variables, you can. Here the T subscript denotes like the total or the tank, and then the V and L subscripts are vapor and liquid. If you want to pause it and solve it, you can. So here's the solved equation. So we use these equations to find the mass fractions, and then it does require the densities, but because we're on that saturation curve, we can just get the densities as a function of temperature. In my program, we just assume the temperature is like the ambient temperature to start off, which is a good assumption. Okay, so now we're actually running the simulation and the tank starts to empty. So obviously as the motor runs, like it uses up Oxidizer, and it ends up being the liquid that actually empties out from the tank because it sits at the bottom and that's where the exit is. So during each time step, some small amount of propellant is removed. If you're not familiar with this calculus notation, m dot is basically the rate of change of the mass, or the mass flow rate. It has units of like kilograms per second or whatever. But since this is a computer program, everything is discrete. Here in the diagram, you can see like some amount of propellant, m dot delta t, is removed per time step. To start the simulation, we subtract mass from the tank, that little m dot delta t, to get our new mass. And then we recalculate the mass fractions because now our total mass in the tank is different. And then we find the change in the vapor mass between the old and the new mass fractions. And basically that just represents the amount of liquid propellant that has to vaporize to fill that empty volume. An important thing, the whole reason we're simulating this is because as some of that liquid vaporizes, it uses energy from the tank, and you end up lowering the temperature and lowering the pressure, which is important for other parts of the engine. So using that change in vapor mass, we're able to find the heat removed from the tank and then find the temperature change, which lets us then calculate the new pressure inside the tank. If you look at the phase diagram again, basically we're moving from the right, whereas like that's close to room temperature, and then it moves to the left as the temperature decreases and the pressure decreases. The next part of the simulation is the injector. Injectors are basically small orifices that connect the oxidizer tank to the main combustion chamber, and their whole purpose is to like atomize the propellants so that they can react better. And then the size of the injector also is what determines like the oxidizer flow rate, which is pretty important for the rest of the engine. They can also be used to throttle the rocket by changing the size of the injector, but currently I don't have like that kind of capability in my program. Here's some examples of injectors with just like water that I think are pretty cool. A lot of them look like shower heads, or sometimes they'll have like impinging streams of propellant that will like hit each other and atomize stuff. Something kind of annoying with the injectors is that there's a pressure drop over them. So it should be kind of intuitive that like as the fluid flows, if you decrease the cross-sectional area, the velocity of the fluid speeds up. If you've ever held like a garden hose and put your thumb over the end and seen that the water like goes out faster, you know, that should be familiar. There's another thing though, that as the velocity of a fluid speeds up, its pressure decreases according to Bernoulli's equation, which is there. And that pressure drop over the injector can lead to vaporization or cavitation. That's especially an issue with our nitrous oxide as a propellant because it's sitting right on that saturation line. So like small pressure drops can just lead to it all vaporizing, and you end up with a two-phase flow through the injector, which is like, there's not great models for, but there are some attempts, which I'll go over. Here you can see a diagram though, like depending on where the vapor pressure sits relative to the pressure before and after the injector, you can see that, you know, whether it'll vaporize or whether it'll stay as a liquid. The fluid flow that we're modeling is really unidealistic because it's comprised of those two phases. There's not really like a great single model that you can use, though there are attempts. In order to make these models work, you have to use empirical coefficients. As seen in this graph, two researchers tried to fit these two models, the SPI and the HEM equations, which I'll talk about in a little bit. They tried to fit them to some experimental data. However, that CD or discharge coefficient, they had to like mess with it a bunch. Those numbers have like no real theoretical meaning behind them. They just kind of figured them out and made numbers that worked. Here are 5 models that I've implemented in my code. You can see the mass flux, which you can just think of as the mass flow rate. It's just the kilograms per like cross-sectional area, and then the chamber pressure. So you can see that some of these better models, like the FML model, the HEM model, and those ones, they show this kind of choking behavior where you have this change in pressure where you have a meaningful increase in the mass flow rate. But at a certain point, you get this choking behavior because gases, when they go through an orifice, once they reach like the local speed of sound, they can't flow any faster, which I'll talk about later with the nozzle. But some of these models attempt to show that, which is why you see that kind of plateauing behavior on some of the graphs. The first model, that's the simplest, is the single phase incompressible. This is pretty standard with just like liquids. It assumes that the fluid's incompressible. All of these like don't really assume any losses from like friction or anything like that. This is actually accurate for like lower pressure drops and with some kind of discharge coefficient that like makes it work. But this is not at all physically representative of what's actually happening. The next model is the homogeneous equilibrium model. It has to do with the enthalpy and the entropy across the injector. It assumes that the fluid is isentropic and then uses that fact to find the mass fractions of the liquid and the vapor. And then you can find the specific enthalpies of those phases because you're on that saturation line. And then it uses the difference in the specific enthalpies to find the mass flow rate. This one like also sucks. I mean, like none of these flow models are that good. So some of the other models that I implemented, the single phase compressible, which is like the SPI model, but it accounts for the compressibility of gases. The next one's the Dyer model, which is literally just an average of the HEM and the SPI models. It's really meant for nitrous oxide tanks that have like extra pressure. So they're not just sitting at vapor pressure, they're sitting above it because you have some other pressure that's like turning all the nitrous oxide into liquid. At saturation pressure, it's literally just an average of the HEM and the SPI. And then the final model is from these Italian dudes called the FML model. It's an average of the HEM and the SPC models weighted by the downstream void fraction with some extra choking stuff to show that effect that I talked about earlier. I don't like fully understand that one, but I implemented it. Here you can see a bunch of different models that exist in literature for two-phase flow. There's also a picture of nitrous oxide like in an injector. This is super cool. Basically all those bubbles are like the fluid cavitating or like vaporizing because of that pressure drop. Using like all of these models requires discharge coefficients, which you have to get somewhere. And there's like limited data for these online, especially some of the more complicated models. There exists like almost no data. There's some for like the SPI, which when I actually design my next motor, I'll probably just end up using that with some crazy discharge coefficient to make it work. But to get an accurate simulation with a new injector though, you really have to get your own discharge coefficients. This involves like some kind of setup to get mass flow rates and also mess with the pressure downstream. I might end up doing it, I don't know. Here you can see a really complicated picture of one. Your setup like would not need to look this crazy. You can make good enough approximations based on similar designs though. As I talked about, there's some data with the SPI model with discharge coefficients online. Okay, so the next part of the simulation is the fuel grain. Fuel grains in hybrid rockets can take lots of forms, but my program assumes that it's a cylindrical grain with a cylindrical port down the middle. That port is where the oxidizer flows down, and it burns from like the inside out, basically. And the diagram on the right, that's an actual fuel grain that I fired and burnt, and then I cut open to look at the cross section. That R dot represents how the radius changes over time. So as you can see in the GIF, basically it burns and that port gets wider and wider and wider. The equation to find R dot has these empirically derived coefficients similar to the injector, except there is lots of data for these online. Those two letters are A and N that are the empirically derived things. This model assumes even regression along the fuel grain, which isn't fully accurate, but it's a good enough approximation. You can see in the real cross section that the regression increases as you travel down the grain, but there's not a lot of good data for adding that to the simulation. So I decided to just assume even regression. So the math behind the fuel regression is actually not that hard. It's just like some geometry stuff with cylinders. Basically, you like find the regression rate using A and N, and then you use the mass flow rate over the area of the port, which is called the mass flux. I talked about that a little earlier. It uses that regression rate to find a new diameter of the port, and then it finds the change in the volume and then multiplies that by the density to find the change in mass. And then using the time step, you can find the mass flow rate of the fuel. At the top of the fuel grain, you have some oxidizer mass flow rate. And then at the bottom, you have that oxidizer mass flow rate plus the fuel mass flow rate. The next part of the simulation has to do with the chamber pressure. I got this part of the model from this program called the Hybrid Rocket Analysis Program. Basically, it treats the combustion chamber like a reservoir. So you have some amount of oxidizer and fuel that enter, and then some amount of exhaust gas that leaves through the nozzle. To complicate things more, the volume of the chamber also changes as the fuel grain burns. Really, the combustion chamber encapsulates like the start of the fuel grain all the way to the like start of the nozzle, because stuff will react as soon as it's in contact, right? As I mentioned earlier, the volume of the chamber is changing. And we can find that pretty easily using the mass flow rate and the density of the fuel. Then we find that the rate of change of the chamber pressure using that equation. Using that, we're able to find a new chamber pressure for our given time step. That M gas there represents like some amount of exhaust gas in the reservoir. So basically like that mass starts to increase and increase, and the pressure increases, which increases the nozzle mass flow rate until eventually everything reaches an equilibrium where you have like the same amount of oxidizer and fuel mass coming in as you have exhaust gas coming out of the nozzle. I'm using this program called NASA CEA, which does like chemical equilibrium stuff to figure out like the temperature of the reaction and stuff between the propellants. It also has some like built-in features that help with the nozzle and the thrust and that kind of stuff, which I'll talk about. This program assumes a convergent divergent or a de Laval nozzle. As you can see, it has a converging section and a diverging section. The M's in the diagram, the capital M's, represent the Mach number. In that converging section, as you travel down it, the Mach number gets closer and closer to 1 until eventually at the throat of the nozzle, or the smallest like diameter part, the flow becomes choked, which means the mass or the Mach number equals 1. And that's like the local speed of sound of the exhaust gas. Once it reaches Mach 1, the flow is considered choked. So if you decrease the diameter even more, you wouldn't actually get an increase in exhaust speed. It would stay at Mach 1. So if you want to increase the speed of the gas further, which we do because that makes our rocket engine more efficient, we have to actually expand the cross section of the flow. So that's why that diverging part is there. And then all that mass exits out the end and is what creates our thrust force. I'm using NASA CEA and then this other thing called prop tools, which basically solve this set of isentropic flow equations to figure out all of the speeds and pressures and densities and stuff in the nozzle. So the inputs into those programs are like the mixture ratio between the propellants, the expansion ratio between the throat of the nozzle and the exit end of the nozzle, the chamber pressure, and then your propellants themselves. Here, the isentropic flow equations that the modules use to actually like solve all the stuff in the nozzle, they revolve around this gamma here, which is the second equation, which is the ratio between the specific heat capacities of the exhaust at constant pressure and constant volume. You can find all these different ratios and stuff, which allows you to ultimately solve for like the mass flow rate and the exhaust velocity. So here's a flow chart representing all of our inputs to NASA CEA and prop tools. You have the ambient pressure, the chamber pressure, the mixture ratio, and then the expansion ratio. Those go into those modules. The big thing that we end up getting is the C star, which is a kind of, it has units of meters per second, but it's kind of like the exhaust velocity. But basically we take that theoretical C star and we use this efficiency called the C star efficiency, which represents like, maybe your propellants don't fully react, or there could be some losses due to like friction from the nozzle or something. And then the mass flow rate is found using C star. In this case, you can think of it as the exhaust velocity at the throat, right? A star is the area of the throat of the nozzle. And to get the mass flow rate there, you do A star times the chamber pressure over C star. The next quantity that's found is the specific impulse, which is like a measure of efficiency of the engine. CF represents, I think it's called the nozzle coefficient, but it's basically like how much more exhaust velocity do you get from the expansion of the nozzle. And then you divide it by gravity. It's kind of a weird thing, but basically you do that so that ISP is in units of seconds, so that you can compare specific impulse across different unit systems. You can have specific impulse in like meters per second and stuff and not have the G there. Finally, we can find the thrust using the ISP and the mass flow rate. NASA CEA also figures out if the nozzle is close to ideal, overexpanded, or underexpanded, which has to do with the expansion ratio of the nozzle and the exit pressure. Here's a diagram of what I'm talking about. You can see when the exit pressure is greater than the ambient pressure, the exhaust still expands a little bit. You basically haven't sucked all of the velocity out of the energy stored in the pressure. If you look up videos of like rocket engines firing in space, they'll always look underexpanded because the correct expansion ratio in a vacuum is like infinite, which is clearly not feasible. You end up with an expanding exhaust gas. The ideal conditions, you can see that the exhaust gas basically goes like straight out the bottom. It's like perpendicular to the exit cross section. And that's when the exit pressure is really close to the ambient pressure. And then overexpanded nozzle is when your exit pressure is less than the ambient pressure, which means that your nozzle has expanded the flow too much and gotten too much velocity to where now you have like a negative pressure difference. You can see that in engines that fire at sea level but are made to go up to where the atmosphere is thinner. Now we've run through everything that the simulation does in one time step. It repeats all of that math we just went through, like a few thousand times, and then you have a finished simulation. But now you actually have to handle the data. So I take all of the data from each time step and put it into a CSV file, which can be imported into Excel and graphed. Quantities like impulse and other things can be calculated by the program. Here you can see impulse. Basically for each time step, it figures out like some small amount of impulse and then it sums them up at the end. Here's like what the output files look like. I just think this looks cool. It's like a bunch of numbers. So finally, I had to validate my program. The best way to validate it would be to have a real hybrid rocket engine with a bunch of sensors and stuff and like compare the data. I don't have that. So the second best method is comparing it to another program which already exists, like HRAP, which I mentioned earlier. You can see thrust over time with a very similar input conditions between my program and HRAP, and you can see they follow a really similar profile. Finally, there are lots of improvements I can make to my program. First of all, my program doesn't go past like, at some point you'll run out of liquid in the nitrous oxide tank and you'll just have vapor left. My program just cuts out once there's no more liquid in the nitrous tank, because like that's where most of your impulse ends up coming from. But you do have some vapor that will empty, so I could implement that. Another thing I could add is heat transfer into the tank. Right now my program assumes that there's no like energy going in or out of the tank walls, which is actually like a decent assumption. But if you wanted to have like heaters or something to keep a higher tank pressure, then you would have to add that to the simulation. Another thing I could add is integrating my program with some kind of like flight simulation. So if you actually wanted to simulate putting this whatever engine in a real rocket and like flying it, seeing like your trajectory and stuff, because the impulse does, or the thrust does change over time, you know, and it changes with altitude and that kind of stuff. So you would have to integrate them. Another thing I could add is a more friendly GUI. That's kind of an extra thing. I don't plan on like releasing this program though, so I don't know how necessary that is. And then a way out there thing would be integrating this program with some kind of CFD software, specifically when looking at like the Injector. That could really benefit from integration with a separate CFD software. I mean, you could do that with the fuel grain and even the nozzle too, I think. But yeah, so that's my program. Thanks for watching. Yeah, comment if you have any questions. I'd love to answer them. I hope to like build more motors soon. Hopefully using this program as a design tool. Yeah, thanks for watching.